Okay, is it recording now? Yes, I think it is. Why doesn't show myself as recording? But okay, so it is recording now, I think. All right, let's get started. Let me share my screen.
Also, I want to ask you a question about the repository. Did you create this repository with rules and
Almost ready. You can start writing notes anyway. It's not a problem. I just
yes, I'm writing now. Yes,
yeah,
yes, I write
I'm
now.
aware that I have to. It's basically set up. I just forgot to email you guys the passwords and all that stuff. So, but it's in a sense it's ready to be used. But I will email you like hopefully very soon. Yeah.
Since I'm a meticulous person and I don't hurry up, or do I need to hurry up for writing lectures?
I mean, it's really up to you. Like probably. I mean, probably it's best not to delay it forever, but it's not extremely urgent.
I make this in my own pace. Yes.
Yeah. Let me maybe ask first a question. If you guys want to stick to the current time, because I did receive some requests to move the talk. Well, as you may recall, today is the first day we have winter time here, or rather, the daylight saving time has ended yesterday. So, and which means that for at least for those of you who do not observe the daylight saving time, the class moved forward by 1 hour. And I received at least some requests to move the class back 1 hour to basically what was the previous meeting time, if you ignore the daylight savings change. So I wanted to collect maybe opinions as to who can or cannot make the time 1 hour earlier. So that's our first question for today. Let's see, how should we phrase it? Maybe can each of you guys leave a comment in chat and tell us whether you are able or not to make the time 1 hour earlier. Let's see. Okay, Jacek is fine, Nivedika is fine, Alonso is fine, Yegor is fine. We have is Arshak fine with this? Yes. Yes. Anybody else? Did we collect responses from everybody? Let's see, 1, 2, 3, 4, 5, 6. Yeah, for those of you who just joined, we are currently discussing whether the class can be moved forward. Moved 1 hour earlier. So what is currently 10 a.m. UTC minus 6, there's a desire to start instead 1 hour earlier at 9 a.m. So if you haven't left a comment yet in chat, please leave a comment in chat whether you can make it or not. Let's see. All right. Okay, so I don't see, I'm looking in chat and I don't see any objections so far. So if there are no objections, I think we can just move it. So maybe I should say next time. by popular demand, we start at, so next time will be Sunday, November 5 plus 7 is 12, right? And we start at 9 a.m. UTC minus 6. Right. That will be, I guess, 3 p.m. Greenwich time or whatever. You can convert to your own time zone. All right. And as usual, I just posted the handwritten notes for today's lecture online at this address. So it's, well, if you want to proceed to the PDF file directly, you can, let me just remind you that there's a PDF at the end. So you are welcome to look at the PDF notes. I know it may be difficult for you guys to, if the slides keep changing, well, these are not really slides, but if I scroll, you may lose track of the previous notes, and this should help you to keep track of what's going on. All right, so I will also try to send out an email just in case somebody is not present today. Okay. Okay, terrific. Let me start the new lecture, and I will continue talking about the functor of points. Let me very briefly revisit what we did last time, which was 2 weeks ago. Last time we decided to develop a formalism where we study a space by launching probes into it. And please insert your favorite analogies with your nation's space agency. So we have and when I say space, I mean sort of slightly. I'm slightly vague here, but imagine, for example, your space is a manifold. So we study a smooth manifold by launching probes into it. And probes, in our case, are objects in the Cartesian psych. Let me align. Meaning the spaces are n perceived as a smooth manifold. So formally speaking, a functor of points f is a contravariant functor f from Cartesian spaces and smooth maps between them, true sets. And morally, you should think of the value of such a functor f of u as the set of smooth maps from u to f. And the value of this functor on a morphism of Cartesian spaces, so let's say u and v are Cartesian spaces, and G is a smooth map from U to V, then f of G will be a map of sets from f of V to f of U. Remember, the functor is contravariant. And morally speaking, it sends an element. So imagine you have an element here in f of V, which morally, you should say, morally is a map from V to some space F that we want to study. Then the map of sets f of g will send such a map H from V to F to the composition of G and H. So you start at U, you apply the map G from U to V, and then you apply the map H from V to F. And our sort of running example was that the notions such as smooth sets and diffeological spaces will be full subcategories of this category of functors from the opposite category of Cartesian spaces to sets. And let me emphasize at this point, which we also discussed last time in some form, that any smooth manifold can be completely reconstructed from its functor of points. So I adopted this notation f with a subscript m for the functor of points of m. So to be clear, so somebody gives you a smooth manifold M and you construct its functor of points, Fm, which sends a Cartesian space U to the set of smooth maps from U to M. And likewise for morphisms. And then you play a game. You say, okay, now I constructed this functor f of m, and I'm going now to forget m completely. So I throw away m. And the question is, can I reconstruct the manifold m from its functor of points, f of m? Or perhaps some functor that is isomorphic to the functor of points, right? So, and the answer is yes, absolutely. And the structure of a smooth manifold, all of its components can be reconstructed from the functor of points. And perhaps the easiest component to explain is the underlying set. So any smooth manifold has an underlying set. And this underlying set, which I call here x, can be reconstructed as the value of the functor of points at R0. So R0 is just a point. And if you look at this description that we had previously, smooth maps from a point into M, that's precisely points in capital M. And therefore, the value of the functor of points on R0 will give you back precisely the set of points in the original manifold. So that part was easy to reconstruct. And what about the rest of the structure? Let me slowly scroll here also. Well, the other part of structure of a smooth manifold, and here it really depends on which of the many equivalent definitions you pick. For example, there's a definition with atlases, there's a definition with the structure sheaf, and one more definition relies on the algebra of smooth functions, and that one is the easiest to describe here. So let me say the algebra of smooth functions on X, so smooth maps from X to real numbers. How can you reconstruct such a map? Well, you have your functor of points, f of m, and you can consider morphisms of functors, in other words, natural transformations, to the functor of points of real numbers. And if you pick such a natural transformation H, well, what is a natural transformation? A natural transformation assigns to every object in your category of Cartesian spaces, so cart, a corresponding map of sets from f of m evaluated in this Cartesian space to f of r evaluated on this Cartesian space. So let's evaluate on R0 the point. Then after you evaluate this natural transformation H at a point, you will get a map of the underlying sets. So the underlying set here will be X, and the underlying set of f of r is just real numbers. So evaluating such H, and maybe I should have spelled this out more explicitly, will give you a map from X to R. And now this stupid thing moved. Ugh. So this gives so H evaluated at R0 will be a map from Fm evaluated at R0, which is just X, to f of r evaluated at R0, which is just R. So that's how you reconstruct all smooth functions on X. And once you know all smooth functions on your smooth manifold, reconstructing the rest of the structure is easy. For example, just to give you one example, how do you reconstruct open subsets? Well, a nice result about smooth manifolds is that open subsets are complements of closed subsets, and closed subsets on a smooth manifold are precisely the zero sets of smooth functions. So therefore, you can reconstruct, and I guess I should be consistent with my annotation, so let me keep this as a subscript. Oops, sorry. Why is this thing not erasing? Like this. So since I already know all smooth functions, I can take an arbitrary smooth function here and take the pre-image under the smooth function of the complement of 0 inside real numbers. And this pre-image will be an arbitrary open subset U of X. And that's how you reconstruct open subsets. So that's how you reconstruct the underlying topological space. And the rest of the structure sort of is reconstructed in a similar manner. All right. Like, yeah, for example, just in case you were wondering how to reconstruct the atlas, you can define local diffeomorphisms just as easily, and then you can say I pick all possible charts. All possible charts will be simply injective local diffeomorphisms, for example, from Rn to your manifold. All of this can now be easily defined using the structure that we reconstructed. Oops. And unfortunately now the page is truncated. Let me maybe try to rescale this. Oops. Oops. Still. Yes, so please select. Oops. What is going on? Now you can see the whole statement. So the formal expression of what we just did is that the functor that sends a smooth manifold M, to its functor of points, Fm, My apologies for the slightly dense writing. Which is a functor from smooth manifolds to contravariant functor from Cartesian spaces to sets. This functor is fully faithful, meaning it is an equivalence of categories when you restrict its codomain to its image. So you take all objects in the codomain that are in the image of this functor, and then you get an equivalence of categories. So
Please some intuition yet to this theorem.
Yeah, so the point is that a priori, you can have two different notions of morphisms of smooth manifolds. And one notion is the usual smooth map. So maybe I should say let me see if I can. Yeah, I think I can insert some lines here. One moment. So a priori, you have two different notions of morphisms between, say, M and, oops. If M and N are smooth manifolds, then a priori, I have two different notions of morphisms. One is just smooth maps from M to N. But now we also have a different notion of a morphism. It's a natural transformation between the corresponding functor of points. So we can say natural transformations from f of m to f of n, the corresponding functor of points. And this theorem tells us that there's a canonical map. And this map is an isomorphism, meaning the new notion of a morphism between smooth manifolds is in fact exactly the same as the old notion. There is no, you don't get any new morphisms between smooth manifolds, and you don't lose any existing morphisms. Everything you had before is exactly what you still have. So this is a crucial property if we are to construct a category that contains smooth manifolds. Otherwise, it would be something really strange. All right, more questions?
Something.
Yeah. In fact, probably at this point, I should also remind you of the Young dilemma. Let me insert one more line. In fact, you know what? Let me just squeeze. Move this down. And now I have free space here. Probably makes sense to also remind you of the Young dilemma. Oops. Which is a very similar statement, and in fact generalizes what we just said. A priori, if I have such a functor f, I have two different notions of, so let's say U is a Cartesian space, and f is a contravariant functor from Cartesian spaces to sets. Then a priori, I have two different notions of morphisms of a smooth map from U to f. And the first notion is what we discussed previously here, when I said that morally elements of f of u should be interpreted as smooth maps from U to F, So that's one candidate for the set of smooth maps from U to F. But now we also have a different candidate, which is the set of natural transformations from the functor of points of the manifold U. Oh, I shouldn't have used F for the same. It's a bit, let me rename this to a different letter. How about G, for example, just so that you're not confused. To G, right? So that's f of u, we know, has the same information as u itself. And natural transformations should be thought of as some kind of smooth maps. So here it seems like I should have smooth maps from u to g. And the United lemma tells you that this map is an isomorphism. So once again, the potential conflict between having potentially two different notions of smooth maps from U to G, in fact, there is no conflict. These two notions are exactly the same. And so that was the United lemma. Let me not, in my experience, it's a terrible idea to try to give a proof of the United lemma. This is something you really should read on your own. And it's highly recommended you read it. Maybe we can include a proof in the notes, but really it's something you should always read for yourself carefully and think about it, because the proof is kind of like a bit tedious, but in a sense very enlightening. All right, so that was the review of functor of points that we did last time for smooth sets. So these pre-sheaves on cart, these contravariant functors from cart to sets are called smooth sets. Well, strictly speaking, I should have mentioned the sheaf condition, but the sheaf condition will be discussed a bit later. So for now, let's just stick with a naive description. And just to remind you of what was the point of all this story, one advantage is that we can immediately gain access to many, many new objects. For example, I just mentioned a couple for you, like the infinite dimensional smooth set of smooth maps from M to N, where M and N are manifolds. But also more exotic objects like the classifying smooth set of differential N forms. And having such objects in your category immediately allows you to discuss, for example, differential forms on the space of smooth maps from M to N, just as one example. And as another example, if you recall what we did last time, I discussed natural operations. Let me show you here. We computed, we looked at morphisms from omega n to omega m and discovered that basically the only such morphisms are given by the Durham differential, possibly rescaled by a real number. And this allows you to immediately define the Durham complex of any smooth set. So the advantage of the functor of points formalism is that a lot of constructions fall out for free together with their formal properties. For example, the Durham complex and the property that the square of the Durham differential is 0, all of this falls out for free now. Compare this with the usual more traditional approach where you try to say we are going to model infinite dimensional manifolds using topological vector spaces. Well, not only is this much more restrictive in that you only get to treat a very small class of objects. For example, omega n is not such an infinite dimensional manifold. It's not modeled on any topological vector space. But also immediately getting a lot of technicalities, very technical arguments concerning topologies on your topological vector space. If you followed what we did last time and today, you may have noticed we don't really talk about topology. Like I mentioned open sets here and there, but we don't really use them. And that's the advantage of function of points, in that it sort of, on one hand, it does take care of the topological aspects, like we treat smooth maps, and smooth maps are implicitly continuous. But on the other hand, it frees you of all the technicalities that would normally be associated with such manipulations. So really, I cannot stress enough how superior this formalism is compared to any other more classical formalism you may be aware of. And of course, probably at this point, we should also mention that there are tons of other examples like schemes and algebraic spaces in algebraic geometry can be defined in exactly the same manner. You replace Cartesian spaces with something called affine schemes. Which are basically, by definition, the opposite category of commutative rings. And this sort of allows you to define the basic objects of algebraic geometry right away and start studying their properties. And of course, even more fancy stuff like skecs, derived skecs, which eventually we'll have to discuss, but let me not overwhelm you right now with technical, with like more fancy notions.
As I understand in algebraic geometry, we take different schemes, yes, and map to sets, yes, in this case, as I understand.
You take schemes, yeah. So affine schemes, yeah. Your probes are now affine schemes, and you study a more generalized space like a scheme or an algebraic space by launching probes into it. So you record the space of maps. In algebraic geometry, these are called regular maps, which basically means polynomial maps in some sense. And you record the data of all polynomial maps or regular maps from an affine scheme into whatever object you happen to be studying. And it turns out this is a surprisingly productive approach. For example, it's very efficient in, say, studying algebraic groups, because that's one of the fastest ways to define algebraic groups. And I'm happy to talk more about algebraic geometry, but maybe not in this lecture, because we should more or less stay focused on what we want to develop for functorial field theory. And as I already mentioned to you, I did omit one important property or aspect of this construction, which is the gluing property or the sheaf property. And we'll discuss it later in detail, maybe not in this lecture, however. But today, instead, I wanted to discuss one more example of a function of points, which will also be used in functorial field theory. And I did promise to motivate every construction I'm going to introduce. So just to remind you, smooth sets are used in functorial field theory in at least two different ways. One is that we need to talk about smooth category theory constructions, where you say, for example, instead of a coproduct indexed by a set, I may want to consider a coproduct indexed by a smooth set. And if you do such construction for, say, vector spaces, then coproduct of vector spaces is direct sum if you index it by a set. but if you index it by a smooth set, it will be compactly supported distributions. And that's something that emerges in a purely categorical fashion from just sheaves without any functional analysis. That's, by the way, another advantage of smooth sets is that they allow you to treat a lot of functional analysis without making, again, without talking about topology, topological spaces. So that's one motivation for smooth sets. The other motivation is that the very notion of a geometric structure will be defined as a pre-sheaf on the side of d-dimensional Cartesian spaces and their open embeddings. And instead of considering a set of open embeddings, you really need to consider a smooth set of open embeddings. And that's essential if you are to prove the geometric cobordism hypothesis. So that was the promised motivation for smooth sets. And I will motivate the next example once we formulate the main theorem that I will give you below. Okay, so our algebraic examples will explain how algebraic structures like groups, rings, modules, algebras, or in our case, I will concentrate on the example of commutative real algebras. So commutative algebras over real numbers. That will be our main running example in this in the rest of this talk. And the functor of points technology says, let's study. Let me scroll up here. Says we are going to study a commutative real algebra by launching probes into it. What are the probes now? So before, probes were like very simple spaces, like Cartesian spaces. Now, probes will also be very simple commutative real algebras. What are some of the simplest commutative real algebras? They are the free commutative real algebras on finitely many generators. And in a slightly less fancy language, these are just algebras of polynomials in finitely many variables. So these will be our probes. And if you launch such a probe into some arbitrary commutative real algebra A here, what are the homomorphisms from the algebra of polynomials to A? Well, if you study a bit of algebra, you know that taking maps out of free objects amounts to mapping generators to your algebra. In particular, a homomorphism from the algebra of polynomials on n variables is completely determined by its values on individual variables, x1 to xn. If you know the value of a homomorphism on every xi, you can compute the homomorphism on every polynomial, because a homomorphism, by definition, preserves addition, multiplication, and therefore all the operations you use for a polynomial are preserved. And the takeaway from this is that the set of morphisms from such a probe, P, to A, is precisely the set of n tuples of elements in the underlying set of A. So just pick n elements from capital A. Okay, so we have this very, very simple description of maps from a probe into A. Let's see now what happens to morphisms of probes. Let's first see what morphisms of probes are more concretely. So you have two polynomial algebras in finitely many variables, namely x1 to xm and y1 to yn. And what is a homomorphism of algebras between such polynomial algebras? Well, such homomorphism is completely determined by its values on variables in the domain, which are numbered from 1 to n, y1 to yn. And for every such variable, I have to construct an element of the codomain. So for each of the n variables, I have to construct a polynomial in m variables on the right side. So in other words, the gauge of f is precisely the gauge of n polynomials in m variables, which I'm going to denote by Rj. So Rj, where j ranges from 1 to n, is a polynomial in m variables x1 to xm. And Rj is precisely the value of f on the variable yj. And according to what we previously described, but maybe I should have said it a bit more explicitly, yeah, somewhere here we should say we are studying functors. Yeah, I guess I gig failed to. Yeah, so let me maybe, yeah, I should have mentioned this before. So let's denote the category of probes as F C alg R, where F stands for free and also finitely many generators, I guess. And we are studying contravarying functors from this category to sets. And such a contravarying functor sends a morphism of probes F to, let me call this, I don't know, G. Then G sends F to a morphism from G of the codomain of F and G of the domain of F. Oops, sorry. I'm sorry, I don't really have enough space to write it out properly, but this is a contravariant functor, so it sends a morphism F to a morphism between the values of G in the opposite direction. So we previously computed that sending a polynomial algebra with n generators gives you the n-fold product of copies of A. So the morphism F, when you apply the contravariant functor G to it, it should give you a map from AM to AN. So let's examine this map in a bit more concrete way. So I'm working with F, which is a homomorphism of algebras from the polynomial algebra on n generators to the polynomial algebra on m generators. And I want to know what does this map do to some element in this set here on the left. So maps from P to A, where P is a polynomial algebra. And I'm sorry, I guess n mutated into m here. So now it will be P. P will be picking out m generators in capital A. So what happens is that GF sends this element P to the composition of these two homomorphisms.
Please, can you repeat about map where we take algebras with subscript and obtain the product of underlying set of A?
Yeah, so here, yeah, precisely. So P is a homomorphism from the polynomial algebra on M generators into capital A, and previously we computed the set of all such homomorphisms here on the left. You can see we computed it as the set of, in this case, it will be m tuples of elements in capital A. And in fact, these are precisely the m tuple. So here I ranges from 1 to m. So I have precisely m elements in capital A. So that's what P gives me.
How can
And
we
then
obtain product?
The product, you mean here on the left?
Yes. This.
Well, that's just another way to say the set of, well, in this case, it will be the set of n tuples of elements of capital A. Right? So
Okay,
this is just,
it is just n tuples.
yeah. So it's the product of n copies of the underlying set of capital A. Yeah, so n times. So that's why the power is n. And if I compose P with F, I get a homomorphism from the polynomial algebra on n generators through capital A, which therefore is described by an n tuple. And let's see what this n tuple actually is. So if I take this composition, P composed with F, and evaluate it on some generator Yj, what I get is a P of F of Yj. And previously, on the previous page, we denoted the value of f of yj as rj, the polynomial in m variables. And so what I get here is a p of rj. So rj is a polynomial in m variables, x1 to xm. And p is a homomorphism of algebras. And homomorphisms of algebras preserve all operations used to define polynomials. So I can pass P inside the polynomial, and P of xi will give you some elements ai in capital A. So altogether, I see that I simply evaluate the polynomial Rj on the elements a1 to am. That's all what happens here. The meaning of this whole construction, the meaning of this structure morphism associated to F is quite simply that the polynomials that constitute F, you start evaluating them on some given elements ai. Let me now spell this out in some concrete examples. Where n equals 1, so you have a single polynomial. R1. And we are looking at a homomorphism of algebras on polynomial algebra on one generator, Y1, into a polynomial algebra on M generators. And this only generator Y1 gets mapped to the polynomial R1. And the function of points formalism tells you that such a homomorphism, such a polynomial, induces a map from AM to A. So the question is, what is this map? Let's look at some examples. Maybe I should scroll here. Imagine, for example, m equals 2. And I will have the polynomial in two variables, x1 and x2, which is simply their sum. Then the corresponding map from A2 to A will take two elements, A1 and A2, as an input and substitute them into the polynomial R. Meaning, this map will be simply the addition map. It takes the sum of two elements of A. Likewise, if your polynomial is x1 times x2, the corresponding map from A2 to A will be the multiplication map, which multiplies two elements. If I take m equals 1, so polynomials in one variable, namely r of x1 equals negative x1, then the corresponding map from A to A will send the some element a1 of A to its negation, minus a1. And a bit more generally, if I pick as my polynomial x1 times some arbitrary constant c, so c is an arbitrary real number. Likewise, I get the operation from A to A that multiplies by c. And as a variation of this example, we can look at the degenerate case, m equals 0. In this case, r will be a polynomial in 0 variables. So a polynomial in 0 variables is just a constant. It's a real number. So here my polynomial is just a real number. And I get a corresponding operation from A0, meaning the set of 0 tuples in A. There's exactly one such tuple, which is the empty tuple. So this set on the left has a single element. This single element, the empty tuple, which here I sort of somewhat perhaps confusingly denoted by a pair of parentheses, because Functorial have a better notation for this, is mapped to the element of A, given by evaluating this polynomial on our variables. We have currently 0 variables. So you simply pick out the element C in A. Remember that capital A is an algebra over real numbers. So perhaps a bit more precisely, I could have written this as C times the unit element of A. So this bold one is a unit element of capital A. So the takeaway from all these examples is that if you're careful at what we did so far, we see that the entire structure of a commutative real algebra can be reconstructed simply by looking at the functor of points, of our original algebra, capital A. So let me maybe scroll here. This. And we can phrase this a bit more formally by the following proposition. A commutative real algebra, capital A, can be reconstructed from its functor of points, which I call again FA. So FA sends a polynomial algebra B, so a free commutative real algebra on finitely many generators, which is B, to the set of homomorphisms of algebras from B to A. So that's the functor of points of capital A. And the proposition states, if somebody gives you the functor FA and does not tell you what capital A is, you can nevertheless reconstruct capital A from its function of points. Let's sort of revisit how this construction works. We pretty much explained how it should work in the previous page, but let me restate it a bit more explicitly here. So the underlying set of your algebra can be reconstructed as the value of the function of points on a polynomial algebra with one generator. Why is that? Well, let's look a bit more carefully back all the way here. I computed the set of homomorphisms of algebras from a polynomial algebra P on n generators as the set of n tuples of elements of capital A here. Now imagine if n equals 1. If n equals 1, then I simply get the underlying set of A. A homomorphism from a polynomial algebra on one generator into A is determined by its value on this generator, which here I call Y. So you get precisely the underlying set of your algebra, which here I denoted by X, just to not to confuse you with capital A. Of course, X will be isomorphic to the underlying set of capital A eventually. Now, next question is how to reconstruct various operations on your commutative algebra. For example, how do you reconstruct the addition operation? Well, in order to reconstruct the addition operation, you will evaluate your functor f and the homomorphism of algebras, like I defined here, is a homomorphism from polynomials on y to polynomials on x1 and in x1 and x2. And it says the generator y to x1 plus x2. And since f is a contravariant functor, it will send r x1, x2 to x times x. That's a set of all ordered pairs in X. And it will send R of Y, as I indicated here already, it will send it to X. That's how contravariant functors work. So evaluating F on this particular homomorphism that I defined here will give you a map of sets from X times X to X. And I claim this is precisely the addition map. And you reconstruct all the other operations in a similar manner, according to what we spelled out on this page here. So you pick a different polynomial like this one, you get multiplication. You pick a polynomial in one variable, you get negation or multiplication by a real number. You pick a polynomial in 0 variables, you get constants in your algebra. In particular, you recover 0 and 1 in this manner. So that's how you reconstruct the structure of a commutative real algebra from its function of points. Any questions, by the way, so far?
As I understand, X is a set of our variables, yes?
X, well, here, yeah, so x1 and x2 will correspond to x1 corresponds to the first component here, and x2 corresponds to the second component here.
Okay, yes. Thank you.
And y corresponds to the sort of x on the right, yes. By the way, can everybody stay for 20 more minutes, or should we finish right now? Is everybody okay with continuing, or because I think somebody may have mentioned to me that they want to finish earlier, but I'm not sure how early that was. Okay, some new messages in chat. One moment. Okay, Jacek can continue. Can everybody else continue? Because if not, we can finish right now and we can continue next time. I can continue.
Go for long.
Say again, Emilio.
I can continue. I can go for however long.
Yeah. Okay. I can also continue. Okay. And the rest is silent. Okay. I didn't receive any objections, so I guess. Okay. Yeah. Thanks. Yeah, we can finish anytime you want, guys. So I try to limit to lectures to 80 or 90 minutes because typically it's impossible to stay focused for more than that. So, but if you are, in case you want more, I can lecture for many hours, but it's probably best if I don't. Yeah, so and likewise, a homomorphism of algebras from A1 to A2 can be reconstructed from the corresponding natural transformation. And probably I should have spelled out what the natural transformation is here. So f of h a natural transformation when evaluated on some probe P, there'll be a map that sends the set of homomorphisms of commutative real algebras from P to A1 to the set of homomorphisms from P to A2. And what is this map? It sends some element G here to H composed G. So you have a homomorphism from P to A1, and you compose it with the homomorphism H from A1 to A2, and you get a homomorphism from P to A2. Then once again, this is exactly how the function of points also work for smooth sets. How we embedded, if you recall, how we embedded smooth manifolds into smooth sets somewhere around here. Yeah, I guess I never really spelled out. I guess it was spelled out on the previous page here. Yeah. Yeah. So same story. And yeah. Okay, so the takeaway from this is that the function of points knows everything about your algebra. Everything there is to know about your commutative real algebra can be reconstructed from its function of points. Let me now supplement this discussion by discussing. So we discovered that all the information is captured in this function of points f, which is a contravariant functor from probes to sets. And there's one more remaining question associated with this, which is, does every functor of this type come from an algebra? And the answer is no, for trivial reasons. And the trivial reasons are very simple. If you look at what previously computed, the value of such a function, if your functor f is the functor of points of some algebra, then its value on a polynomial algebra with n generators will be the n-fold Cartesian product of its value on an algebra with one generator. So there's a non-trivial restriction, which is the values of this functor on polynomial algebra with n generators. They are not arbitrary, they are just the n-fold Cartesian product of some fixed set. And categorically, this is expressed by saying that the functor f must preserve finite products. So let's examine what finite products are in these categories. Well, we know what finite products of sets are. These are just the usual Cartesian products of sets. What about finite products in the domain category? So FC ouch up. Well, products in the opposite category are coproducts in the original category. And coproducts in the category of commutative algebras are precisely the tensor products of algebras. The universal property, this is a nice exercise to check that the universal property of tensor products of algebras, commutative algebras, guarantees that it's precisely the coproduct.
Is some kind of observation, or we state this strictly about preserving finite products and coproducts?
Yeah, must preserve finite products, I guess, up to an isomorphism. Not strictly. So the point is, if the functor f is the functor of points of some commutative real algebra, then this functor must preserve finite products up to an isomorphism, which we will see shortly how it is established. That's a property of the functor of points of any algebra capital A. So imagine you have an algebra capital A, and we examine its functor of points, how it behaves on coproducts of such algebra, which we just discovered are tensor products. So this is a coproduct. So if I tensor together two polynomial algebras and finitely many generators, I of course get a polynomial algebra on as many generators as there are in both of those algebras. And this allows me to compute the set of homomorphisms in two different ways. One is that the set of homomorphisms is just a to the power m plus n, so the set of m plus n tuples, because of this complication that the tensor product of the polynomial algebra on m generators and n generators is the polynomial algebra on m plus n generators. But on the other hand, the universal property of coproducts guarantees that morphisms out of a coproduct into some fixed object can be equivalently rewritten as the product of the corresponding sets of morphisms. And here the set of morphisms will be the set of m tuples in A, and here the set of morphisms will be the set of n tuples in A. So we see that in general, for every functor of points, we expect that it sends coproducts to products. And if we now incorporate this condition in the codomain category, so meaning we don't just land in the category of all functors from all contravariant functors from polynomial algebras to sets, but rather in functors that preserve finite products, which I indicated by this red cross here. So red cross means preserves finite products.
Sorry, stupid question. Should it really be a tensor product or the direct sum? Because the dimension would be n times n, right, for the tensor product?
Well, you are probably thinking about the tensor product as let's see, as vectors. Let's see, one moment. If you tensor these two vector spaces as the tensor product as a vector space will be the vector space with a basis being the product of bases. And then, of course, you will have the product of dimensions. But here, maybe I should spell it out slightly more carefully. Let me maybe insert a page here just so that it's perfectly clear. One moment. So let's spell it out a bit more explicitly. So what happens when I tensor together, let me use black, the polynomial algebra on M generators and the polynomial algebra on N generators. Well, let's identify the Gregor components of these algebras. In degree 0, we just have real numbers. In degree 1, we have monomials, so monomials of degree 1. That's just a vector space with a basis. And here, I guess I really should pick a different notation for a vector space with a basis. Let me use angle brackets. So this is a real vector space with an integrated basis. And likewise, on the right side, I have real numbers and a vector space with a basis of monomials. And in degree 2, I have a vector space with a basis of monomials in degree 2. So these have a form xi, xj, and in order to avoid repetitions, let me say I is at most j. And likewise, here I have a basis of monomials of degree 2 with the same restriction. What happens if we tensor two such algebras together? Well, let's recall that the component, for the tensor product in degree, say, R, it will be the direct sum. Maybe I should not, maybe I should spell it, let me use a proper notation. So I'm tensoring two Gregor algebras, let's say A and B together. And in degree R, I will have a direct sum of A, let's say P tensor BQ, where P plus Q equals R. That's how Gregor algebras are tensored. So the component in grading R will be all possible tensor products of the corresponding Gregor components of A and B tensor together, and then you change the direct sum. So let's see what happens in our case. In degree 0, there is only one way to get 0 as a sum. It's 0 plus 0. So this will be R tensor R, which is R. In degree 1, and now let me scroll here so that we can see both at the same time. In degree 1, I have either 0 plus 1, which will give me this, or 1 plus 0, which will give me this. So I have this vector space tensored with degree 0, which is just real numbers. Direct sum, the other tensor product, R tensored, and let me put parentheses here so we don't, this vector space here. Let me just say yj, because so tensoring with real numbers doesn't do anything, so you get back the same vector space. And here you also get back the same vector space. So what happens when I get the direct sum of two such vector spaces? I get the direct sum, the vector space with a basis precisely of all monomials of degree 1, like this. So now you can see you can see that in degree 1 we get m plus n. And if you continue this story in higher degrees, for example, in degree 2, I will have 0 plus 2, 1 plus 1, and 2 plus 0. So I will get, so from 2 plus 0, I will see monomials xi times xj. Direct sum. From degree 1 and degree 1, I will see the tensor product of degree 1 and the degree 1. So this will be, well, let me write it as a tensor product, or why not? Xi tensor R yj. And finally, from 0 and 2, I see these monomials here, R, Y, I, Y, J. Sorry, it doesn't really fit. Now, what is this tensor product here? Well, this will be precisely, let me write it down, the direct sum. So here I have as many basis elements as there are pairs of basis elements in the first factor and the second factor. So of course, these will be precisely the monomials of the form xi times yj. And finally, for the last summing, I see yi, yj. So that's how you get all monomials of degree 2. Yeah, so that's why when you tensor two polynomial algebras on m generators and n generators, you get a polynomial algebra on m plus n generators. All right. Okay, any questions remaining about commutative real algebras and how to work with them using the function of points? All right, so let me now maybe like explain what is the point of all of this, because previously we get smooth sets and we discovered some very obvious benefits, such as being able to work with infinite dimensional mapping spaces, being able to define differential forms on such spaces, and so on and so on and so on. But here you see this theorem tells you have an equivalence of categories, so you don't really see any new objects here. There is nothing new here. It's just a tautological reformulation of something you already know perfectly well. And what's the point of all of this? Like, there's nothing new here. But in fact, this approach allows you to immediately get something very new. If you look more carefully at this site here, the opposite category of finitely generated commutative real algebras. And the observation to make is that, let me sort of formulate this as a proposition. The opposite category of finitely generated free commutative real algebras is equivalent to the following category, which I call the category of Cartesian spaces and polynomial maps. Its objects are just the spaces Rn, for n greater than or equal to 0, And its morphisms from some Rm to Rn are polynomial maps. And just in case you are wondering what exactly is a polynomial map between two vector spaces, well, a polynomial map has n coordinates, and each coordinate of such a map must be a polynomial map in m variables. So altogether, you see n polynomials in m variables. That's what a polynomial map from Rm to Rn is. Now, if you recall when we talked about homomorphisms of probes, right here, we make an observation that a homomorphism from a polynomial algebra in n variables to a polynomial algebra in m variables is precisely given by the gauge of n polynomials in m variables, which, if you compare with this side, you see it's essentially the same thing, except that here m is on the left and n is on the right, and here n is on the left and m is on the right. So that means this functor, you must put an opposite here because it's a contravariant equivalence. So this category that we used many times, in fact, has a very nice and very geometric description. Just Cartesian spaces and polynomial maps between them. And of course, such a description immediately opens up a possibility of replacing polynomial maps with smooth maps. And this will be a completely new object. And in fact, let me spell this out explicitly as a definition, and this will be a good point to stop. The category of what is called traditionally called C-infinity rings is, by definition, the category of product-preserving functors. The category of finite product-preserving functors from Cartesian spaces and smooth maps through sets. So in maybe formulas, the category of C-infinity rings is by definition the category of finite product preserving functors. Let me remind you that you really need to put this cross here. From Cartesian spaces through sets. Notice there's no up here because if you look here, up is now hidden in the geometric description, right? So on the right side, you have a geometric category of spaces. On the left side, you have the opposite category of corresponding algebras. So we hid the up into in the geometric sort of side. And this is a really exciting development in a sense that now we really can motivate this in a sense that just like commutative algebras form the appropriate setting for algebraic geometry, and they give you the appropriate notion of a ring, or equivalently an affine scheme for algebraic geometry. C-infinity rings give you the appropriate notion of if you want a smooth ring or a ring with a smooth structure for differential geometry. And the advantage of this, like this has many advantages, which we will discuss next time, but such a definition can only be given through the formalism of functor of points, because otherwise it would be quite impossible to guess what it should be. Next time we'll spell out carefully many consequences and properties of this definition. And this will be useful for functorial field theory, for example, in a sense that, I promise to do motivation for everything we introduce. So such generalized rings are useful for functorial field theory because, for example, they allow you to talk about deformations of functorial field series. Just to give you maybe some, like for example, in quantum field theory, you want to talk about perturbative QFT, which is a way to sort of study deformations of so-called free quantum field series. And deformation here, really, in our setting, once we introduce those infinity rings, it will be a space sort of whose algebra functions, for example, so it will be controlled by a space whose algebra functions, for example, is maybe something along the lines of Jake polynomials, and set the n plus first power of epsilon to 0. So this will control the nth order infinitesimal neighborhood. Or you can, in fact, take the whole formal series, which will also be a C-infinity ring. And this will control the so-called formal neighborhood. And finally, you can take an even bigger ring, take smooth functions on the real line, and mod out by the ideal of functions I, which vanish outside of some neighborhood of 0. So I is f from real line to real line, such that there is an epsilon greater than 0, for which f restricted to the interval like this is 0. Sorry, I meant the opposite. I apologize. F restricted to the interval from minus epsilon to epsilon is 0. So you identify two functions if they coincide on some neighborhood of 0. So that's also known as a germ of a function at 0. And this is what I would call a germing neighborhood. So the point is that deformations of functorial field series will be controlled by appropriately designed C-infinity ring. And at least in the last example, it is truly essential that we have a C-infinity ring, because we really are talking about germs of smooth functions, and it's not really possible to treat it in any way other than a C-infinity ring.
As I understand that this rings is encoded perturbative quantum field theories, yes. What's about non-perturbative quantum field theories?
Well, the formalism that we will be defining will be by assumptions, so to say, non-perturbative. And the point is, like, if you say, okay, I want to study some perturbative phenomena, mathematically speaking, this amounts to computing what is called the cotangent complex, or if you want a bit more roughly, the cotangent space to the moduli SCAC of non-perturbative functorial field series at a point given by some free functorial field series. So in general, the perturbative expansion starts by identifying a particularly simple quantum field theory known as the free quantum field theory, and then it studies infinitesimal deformations of the action. So it adds infinitesimal deformation of what is called the interaction term, and studies how the functorial field theory changes when you deform the Lagrangian in this manner. And these infinitesimal deformations were sometimes you would call the infinitesimal parameter h, or I mean, of course, mathematically I talk about epsilon, but in physics you would call this h bar. That's what controls your perturbative expansions. Yeah.
I was just going to ask about what's written on the right-hand side. These are all sort of constructions on the algebra side, right? On the C infinity ring side. Is there
Yeah.
like a nice geometric interpretation for these? Like, are they related to jets? Maybe.
Yeah, no, of course. The point is like maybe let's start with the unrestricted algebra of polynomials, for say, right? R of x. That's basically the algebra of polynomial functions on the whole real line. Somewhere here you have 0. What happens if I start, and of course you can also say the same thing about smooth functions, right? Smooth functions of one variable, that these are functions on the real line. And the point is, like, if you mod out by some ideal, like say this ideal I, where you say, okay, I'm going to identify two functions if they coincide on some neighborhood of 0. What this means is that any information outside of this neighborhood becomes irrelevant. So the whole real line now disappears, and what you see geometrically as a space that remains after modding out this ideal I, well, geometrically it looks like a germ. Well, take 0 and take the germ, infinitesimal germ of 0 inside the real line. So you literally think about it as, if you want, the intersection, so to say, of all open intervals that contain 0. And of course, classically speaking, this will be just a 0 itself. But if you work in the function of points formalism and enlarge your category, your site, to the site of the so-called C-infinity schemes, in the category of C-infinity schemes, you can compute the intersection of all open intervals around that contain 0, and you will discover that it will be precisely this germy neighborhood of 0. And this is something we can do later, maybe next time, as a little example that tells you why you get something which is not just 0, but more. And this germy neighborhood in itself contains an even smaller neighborhoods. First, there's the so-called, well, I don't even know how to depict it, but the formal neighborhood. Which only, so the germy neighborhood remembers the whole germ of a function, of a smooth function. The formal neighborhood only remembers the Taylor series, which is less information about a smooth function. And this formal neighborhood contains the infinitesimal neighborhoods of finite orders, which only see maybe information about the first k derivatives. For example, the first order neighborhood will see the first derivative of your function and nothing else. So geometrically speaking, all those algebras are algebras of functions on spaces that have a single point, and a small tiny germ around this point. Okay, any more questions? Okay, if not, then I guess that's it for today. And next time I will see you in 1 week from now. But remember about the time. So we agreed for, just to remind you guys, we agreed for 9 a.m. Yes, so 9 a.m. UTC -6, 1 hour earlier than we started today. And I will try to send out an email about this. So
Is this new meeting time for the rest of the term, or is this just for next time?
I think it will be a fixed, yeah. So it's not just the next time.
Okay.
I should
Okay.
say new time, new
Yeah.
meeting time will be this. From now on, yes. I mean, basically it's the same as the old time if you ignore the daylight saving switch, because the solar time will be the same. So if any of you guys are not observing the daylight saving time, like I think most countries outside of the US and Europe do not, then you will not see any difference from what we had before, except for today. Okay, more questions? And yeah, I'm sorry, I will finally set up the repository and I will email you guys with details, but you can still type notes in later. I mean, we can decide how to combine them later. By the way, who wants to type today's talk?
I can type it.
Okay, yeah. Okay, great. Thanks a lot. Yeah, so okay, then I guess that's it for today. If you guys have any questions, do feel free to ask, but otherwise, that's it for today.
All right. Thanks. Have a good
Yeah,
afternoon.
yeah,
Thank
too.
you. Bye bye.
Bye.
Дмитрий Станиславович, а можно ли с вами через где-то час поговорить?
Ну да, через час 20 минут, через полтора часа, скорее, я бы сказал так, да. И пошлите мне сообщение просто на мой телефон. У вас есть e-mail адрес, который это может делать.
А вам как удобно, через час или через полтора? Через полтора удобно, да, будет вам?
Ну,
как
видимо,
бы,
скорее через полтора, видимо. Ну, вы можете просто мне послать текст.
Я
Ну,
вам тогда в 10 где-то напишу примерно. Сейчас вот без 29, я вам тогда в 10 где-то напишу тогда.
Ну, да, сейчас у вас, да, у меня сейчас без 20:12. Мы можем поговорить, не знаю, в час, примерно в час 20, час 10, час 20 я должен освободиться.
Да, хорошо. Я вам тогда, да, через полтора часа, получается, через полтора, через час 40 где-то напишу.
Мгм.
Спасибо.
Хорошо. Да, тогда все. До свидания.